Carlos, an instructor from Durham School, said he spent his whole life developing a single idea about the universe. Now that it's being tested, he's all for it because that's how science moves forward. He thinks the James Webb Space Telescope is a game-changer, seriously messing with what we thought we knew about the cosmos. A new super-deep image shows we've got some stuff wrong in cosmology. The telescope, which was supposed to show us the first stars, is actually going against old views and could give us some crazy new science. Not everyone's scared of these new facts. Some experts are happy about the changes because it's been clear for a while that something was off with our old idea. The difference in opinions about how fast the universe is expanding should have been a red flag, but people stuck to old theories. The cosmic microwave background, CMB, radiation, thought to be the oldest light in the universe, was made around 380,000 years after the Big Bang. That's when the universe cooled down enough for electrons and protons to make hydrogen particles. Researchers call this reionization, which made the universe see-through. The CMB was first spotted in 1964 by Arno Penzias and Robert Wilson, American physicists who were working on radio antenna stuff. This find was seen as strong proof for the old Big Bang theory, earning Penzias and Wilson a Nobel Prize and a spot in astronomy history. The CMB probably gives us a peek at the early universe, with small temp differences giving us key info about the conditions soon after the Big Bang. Experts used the CMB as a way to check basic measurements of the material universe to see how fast it was expanding, among other things. Edwin Hubble had already figured this out in the late 1920s, finding that far-off galaxies are moving away from us, and their speed depends on the distance. Today, this is known as Hubble's law or the Hubble constant. Hubble didn't have the fancy measuring tools we have now. When the CMB was found, it led to a recalculated expansion rate. These were lower than Hubble's first number. Later, experts recalculated the rate using Type Ia supernovae as standard candles, giving stable light that could be used as a reliable measuring point. The CMB estimates gave an expansion speed of around 67 km per second per megaparsec, while estimates using astronomical blasts gave around 74 km per second per megaparsec. So, what does this difference in expansion speed tell us? This goof has been known since the 90s. Since then, analysts have known, or at least thought that, something might be the matter with the examination of the CMB, the assessment strategies, or the possibility of the universe's extension. The difference between the observed and predicted values of the expansion rate is known as the SAA strain or Hubble strain. The effects of this strain are huge, showing that basic pieces of how we get the universe may be wrong. For a while, experts were confused. But since the James Webb Space Telescope started working, it's given experts amazing info that might shed light on the expansion speed issue, with systems so old and mature that their growth should have started before the Big Bang, messing with old cosmology. Analysts now talk about a crisis in current stargazing. Not only could the improvement rate be off, but the whole idea of improvement or the Big Bang itself is being questioned. Pictures from the telescope give proof of a universe completely different from what we've long thought. The SAA pressure was the chief scold to specialists who still have faith in old speculation. Now they face an issue. Do we really get the universe? Other researchers stand on the remnants of their once brilliant source of both discovery and torment, exploring in space with fear and wrestling with what they find, taking into account the emergency in science. We should ask ourselves, what do we actually know about the universe? To answer this, we need to get how science works. Experts use math models, data, and smart thinking to move ends from the general to the specific. Their understanding comes from insight, credit, results, and assessments. The word theory itself shows that these are advancements in thoughts, not facts. The main data we have are the photos telescopes give, the sound waves and radiation gathered with radio telescopes, and the latest data from neutrino studying systems or gravitational wave indicators. With the James Webb Space Telescope, we now have a tool that can split light into frequencies and break it down in amazing ways. Webb can show us the main part of galaxies in the early universe, how much mass they had, and how many stars were there. It can also follow the shape and course of a galaxy's growth. Webb has limits, though. For example, it can't always fully decide if we're seeing galaxies or black holes with immense gravitational forces that shine as brightly as a galaxy. We should face the fact that our science has long accepted potential results as facts while ignoring other CL explanations. Research has been sure about its accuracy. The latest finds from the James Webb Space Telescope are key signs to replace theories with new insights, just like in science. Analysts are waiting for new finds, which are surprisingly different, and experts are working to come up with new explanations. The new reveals shake the base of our science, bothering many experts. The current models of real science are still based on Isaac Newton's laws from the 17th century. His laws of motion and gravity were the base of our understanding of the reality of this world and the universe for a long time. Newton's principles describe the movement of objects under normal conditions and work well on Earth. But in space, his idea needed work, mostly done by Albert Einstein in the early 20th century. Einstein's special theory of relativity, released in 1905, changed how we saw reality, showing that events are related and depend on the observer's movement. His general theory of relativity, released in 1915, extended this idea with math looks at gravitational traits based on the curve of spacetime by masses like stars or galaxies. Einstein's principles and ideas were key in many areas, but he knew their limits. He knew his theory would never fully describe the universe and wanted to see a unified theory, which he never got. No other expert has reached this stage either. Wouldn't it be cool to know where it lies? Michio Kaku, an astrophysicist from the USA, said in an interview that addressing this issue would win a Nobel Prize. Could we find whether the experts might have missed potential misinterpretations or whether our telescopes are to blame? Dark matter and dark energy are suspects for the key reasons for the cosmological situation. Our growing models of the universe include ideas that dark matter and dark energy make up around 95% of the universe. But neither has been seen, and their presence has never been shown. They probably don't exist in any form, requiring alternative explanations for the universe's expansion and the dynamics of galaxies. On the other hand, they could have properties we don't get yet. One thought is that the true properties of dark matter and dark energy have changed over time, potentially showing some type of growth. Gravity is another idea to test. This force, which creates attraction through mass or curvature in spacetime, hasn't been fully explained. The ideas of spacetime, which come from Einstein and have been upheld, may need another look. We can't rule out that gravity has shock properties or that another force is responsible for the gravitational attraction between objects. Some constants have been set in cosmology and astronomy as universal principles. The study of the universe has been defined by our search for understanding and discovery. From ancient human cities watching the stars to space telescopes exploring the depths of the universe, each step has revealed new mysteries while challenging beliefs. In cosmology, the James Webb Space Telescope, JWST, is of our scientific way, likely to change how we see the universe's origins and growth. Run with amazing Webb is a leap forward in science, designed to look further into the universe than ever with accuracy. In radiation, the CMB offers a look at the universe as it existed after its first with the world. This form of radiation carries info about the universe's early conditions, including its temp changes, which are to get the growth of galaxies and large-scale structures. The values of the Hubble constant, known as the Hubble strain, has been a subject of debate. That something is wrong with the universe and its early structures. New theories require of our own expansion. New hidden parts of the universes, raising about dark matter and dark energy, two that make up most of the of science on to reshape our theories. Webb's will is for future and shed light on new on the universes. The future of cosmology might changes, too big for how we see the universe from the Big Bang to that its fate. To the questions may our Webbs may be to that could how we see itself. The way for cosmology and space science is with each new piece of data from telescopes like Webb as to the questions has ever asked. How did the universe begin? What is its fate? Are there other forms of life out there, or are we alone in this universe? These are questions that may one day find answers, and the James Webb Space Telescope is at the very of this effort. The future of cosmology will have new technologies, theories, and that to the of what we know. As we further into one thing is clear, science, like the universe, is an of, driven by the for, and the of. The SAA pressure was a warning sign to experts who still trust old theories. Now, they face this question, do we really understand the universe? Some researchers are struggling with what they find. Considering the crisis in science, we should ask ourselves, What do we really know about the universe? To answer this, we need to understand how science works. Theoretical experts use mathematical models, data, and smart reasoning to draw conclusions. Their understanding comes from a mix of insight, results, and evaluations. The term theory itself shows that these are ideas, not facts of information. The main data we have are the photos telescopes provide, the sound waves and radiation collected with radio telescopes, and the data from neutrino studies or gravitational wave detectors. With the James Webb Space Telescope, we now have a tool that can split light into frequencies and analyze it in amazing ways. Webb can show us the first parts of galaxies in the early universe. However, Webb has limits. For example, it can't always tell us if we're seeing galaxies or black holes with huge gravitational forces that shine as brightly as a galaxy. We have to admit that our science has long treated as facts, while ignoring other explanations. Research has been too sure of itself. The latest discoveries from the James Webb Space Telescope are science to replace theories with new ideas. Analysts are excited about the new findings and are trying to come up with new explanations. The new discoveries shake the foundations of our science, upsetting many experts. The current models are still based on Isaac Newton's laws from the 17th century. His laws of motion and gravity were the foundation for our understanding of this world and the universe for a long time. Newton's principles described how objects move under normal conditions and work well on Earth. However, Einstein changed them in the early 20th century. Einstein's theory of relativity, published in 1905, changed how we interpreted reality, showing that events are relative to each other and depend on the observer's movement. His general theory of relativity, published in 1915, expanded on this idea with mathematical models of gravitational traits based on the curvature of spacetime by masses. Einstein's principles were in areas as well, however. He realized these limits. He knew his theory would never fully describe the universe and wanted to see a unified theory, which he never achieved. No other expert has reached this stage either. Wouldn't it be cool to know Mio Kaku, an astrophysicist, said that solving this issue would win a Nobel Prize? Could we explore whether the experts might have missed some potential misinterpretations or our telescopes are to blame? Things and matter and energy are likely the reasons for the cosmological emergency. Our models of the universe say that matter and energy make up about 95% of the universe, but neither has been directly seen. They might not exist in any form, which would mean we need other explanations for the universe's expansion and the actions of galaxies. On the other hand, they might have traits we don't yet understand. One idea is that the real traits of matter and energy have changed over time. Gravity is another hypothesis to be tested. This force, which creates attraction through mass or curvature in spacetime, hasn't been fully explained yet. The ideas of spacetime, which come from Einstein and have been supported, might need to be revisited. We can't rule out the chance that gravity has surprising traits or that another force is creating the gravitational attraction between objects over time. Some constants have been set in cosmology and astronomy as principles. The study of the universe has always been a mission defined by our constant search for understanding and, from civilizations watching the stars to space telescopes exploring the depths of the universe, each development and theory has revealed mysteries while challenging beliefs. In cosmology, the James Webb Space Telescope, JWST, of our scientific progress should to change the universe's end. With incredible JWST and space science that's to look into the deeper than ever before. Within CMB the Big Bang a universe is it after it's with the carries about the universes it's which are to the of galaxies and structures. The invalues of the Hubble been a subject of debate. It that with our the universe and its challenges and of our own. New rays about matter and two components that make up of. The of depends on the two are and of new. Webb should light on new on the universes the of might see leading to for how we the universe. The to the most may beyond our. Webb's may be anew that how we itself. The foreign science is with each piece of data from telescopes like Webb's to the most has ever asked, how did it begin? What is it to their other forms of life? Are we alone in this universe? These are that may one day and the James Webb Space Telescope is at the of this effort. The of will of new refined in that to the we know. As we further into the one thing is certain, science, like the universe itself, is always changing, driven by the for and the of creation.